Okay, good morning everyone. Welcome to your Physics 211 course, and we're going to begin the course from Chapter 2. So Chapter 2 is about motion along a straight line. So in this chapter, you're going to learn about the definition of position, what is a position vector, and also how do you do what is the definition of displacement. And you're going to learn the definition of velocity, acceleration, the average velocity, the average acceleration, instantaneous velocity, instantaneous acceleration. And then we're going to go, and then after that, we're going to go over the special case when you have the acceleration that is a constant. And based on the constant acceleration, there are three equations of motion that can be deduced, and you're going to learn about that. Okay, so what is a motion? So let's say you have a particle or an object that's moving along, moving somewhere. So we need to define the position vector. So we have, for example, let's say we define this. This is your x-axis. And you can define your reference point. This is your 0, so that's your reference point. And you can have an object that, say, initially is moving from the origin and then moving at a pace, and then at some point is stop at x1, and it takes time t1. And then it's moving from this point to another position. So this is your x2, and the time here is t2. So we can see that on the x coordinate, the object initially go from 0 to making a stop at this point and start at that point. So this x1 and x2, we call that position. Okay, so these are the position that you know where the object is at at certain time, and then. What is the displacement? To find the displacement, let's say if you look at the object from x1 to x2, what is the displacement and how to express that? We use this symbol delta x, which is the difference between the final position and initial position. And when you have delta x, your delta x is always taken, you're always going to use the final position minus initial position. So in that case, you have your x2 and then minus x1. So this is your displacement. Now displacement and position. So displacement and position. So position and displacement, they both are vectors. So what are the vectors? We're going to discuss more in details about vectors in Chapter 3. But suffice to say that vector comes with the magnitude and direction. So we know that this object going from x1 to x2, so it comes with the magnitude, the distance, the displacement, and also the direction. So it's going rightward instead of going leftward. So vector comes with a magnitude and direction. Okay. Now through our physics courses, we're going to use SI unit. So what are the SI units? So for the SI unit, that's the standard international system unit. So for SI unit, that's a mass. For mass, we use kilogram. This is the standard SI unit. Now for distance, we use meters. Okay, and for time, we use seconds. So these are the standard SI unit that you're going to use a lot. And then sometimes the units are not given in this SI unit. Then you need to know how to convert those units. Most of the time, that say if you have so there are letters that indicate the factors. So K is 1,000, multiplication of 1,000, and M. Capital M, that gives you 10 to the 6. And the little m, the lowercase m, that is 10 to the negative 3. And then you have your centimeters, which is a commonly used. Centimeter is 10 to the negative 2. So, for example, let's say you have 1 centimeters. How do you convert it to meters? You have to convert it to meters because centimeter is not an SI unit. So that will be 10 to the negative 2 and then meters. Okay? So that's basically how you do the conversion. Let's say you have 1 gram a gram is not an SI unit, so you have to convert it to kilograms. So this will be 10 to the negative 3, and then kilograms, okay? As you can see, the kilo, so that's 1,000. And so that when you have negative 3 times 10 to the 3, that gives you grams. So this is how you do the conversion. All right, so you have the displacement. So displacement is defined as delta x, that is x2 minus x1. So we might have, so let's say if you have an object, as I mentioned, displacement is a vector. It comes with the magnitude and direction. It's always the final position minus the initial position. So let's say this object initially at x1, and it moves to x2, and then it goes back again. So what will be the displacement for that case? So you start from this point, go here, and then turn back. And as you can see, the displacement is the final position minus initial position. So if you use the definition, the displacement would just be x1 minus x1 because it goes back to its original place. So in that case, the displacement is actually 0. Now we can see that this displacement is 0 does not mean that the total distance is 0. What is the total distance? The total distance will be from this position to that position, whatever distance that you have, and then you have this back to this. So that will be for distance. For distance, the total distance, it would just be 2 times whatever the difference of x1 and x2. This is your total distance, and you can see that it is non-zero. But then when you thinking about the displacement, that displacement is actually 0. So that's the difference between difference between total distance and the displacement. Okay, so that's an important important difference between that. Now we define, so you can see that this is rightward. So everything, so we define this to be like that. We need to define a sign. Rightward, upward, they're all positive. And if an object is moving leftward and downward, we associate that with negative sign, okay? So that's if you have an object that's moving to the left, it means that the position vector will be negative. If it's moving downward, which means that the position vector is also negative. Okay, so you have to actually put a negative sign in front of it to let people know that it is moving leftward or downward. Okay, now, so we have this displacement. How do we define average velocity? In other words, when you have an object moving from x1 to x2, what is the average velocity? So by definition, the definition of average velocity is that it is a ratio. It's a ratio of total of displacement to the time that it took for that displacement to happen. So the AVG, the average velocity, is defined as, okay, use a lowercase. So AVG, that's equal to displacement, so that's delta x, over the time, delta t, the time interval that the displacement took place. So in this case, we know that your delta x would just be the difference between the final position and initial position and over that time interval that's say t2 minus t1. Okay, so this is the definition of average velocity. When it comes to average velocity, sometimes we're not really interested in knowing the average velocity. We're more interested in knowing the instantaneous velocity. So in that case, how do we find the instantaneous velocity? The instantaneous velocity, which we just drop the AVG and we just use the V here. And in fact, velocity is a vector as well because we're doing one-dimensional. So I did not draw the vector sign. To be rigorous, you have to draw like that. Okay. So anyway, but then we can discuss that in chapter 3. So what is the instantaneous velocity? Instantaneous velocity can be found if we actually shrink the time so that, and then find out what is the displacement that took place during that time, which is approaching to 0. So using mathematics, so your delta t when you approach to 0, which you'll narrow the gap of time interval. And then you have this delta x over delta t. Now, everyone who has learned calculus will know that when you have this expression that you have delta x over delta t, and when the delta becomes very small, then it becomes dx dt. Okay? So your dx dt, that's just the time, the differentiation, of the position versus, with respect to time. So this is what we call the instantaneous velocity. And just by looking at this, we know that both the average velocity and instantaneous velocity, they have unit. That will be meter per second. These are the SI units, okay? So if we were to graph this, let's say you have the position, you have the time, and you have an object that's initially from going as a function of time, is going from, let's say, here and there. So let's say this is your x1, and then this is your x2, okay? So then, when the object is at x1, the time is at t, I'm sorry, I had it reversed. So this is your x1. So this is your t1 and t2. So t1 and t2, and this is your x2. So just by looking at this, the average velocity basically is the slope from this point to that point. So you can see that you connect those 2 points and find out what the slope is, right? Because that's the definition of slope on this xt diagram. You have the separation, the difference between the two positions and the difference between the time, and you take the ratio. That just gives you the slope. Okay, so you can see that this is if you relate this equation to the what's going on the graph, this is basically what it is. Finding the slope on the curve, on the xt curve. Okay. So now, let's say, so this is the average velocity. Like I said, velocity is a vector. So you have the vector sign, so this is a vector. There's another quantity, we call that average speed. What is the average speed then? We use S to indicate that's average speed. So the average speed is equal to the total distance. See, now we're not using the displacement, we're using total distance over the total time, delta t. Okay, so take for example, let's go back to this, this previous, case example that we mentioned. So in this case, what will be the average velocity? And is it the same as the average speed? If you have an object initially at x1 and then go to x2 and then turn back to x1, what will be the average velocity? So the average velocity in this case, as we already shown that your delta x is actually 0 because you're going back to the original starting place. So if your delta x is equal to 0, which means that your average velocity is actually 0 because you have 0 displacement. What about your average speed? For the average speed, we know that the total distance is not 0 because you go from this point to that point and back to that point. So it's 2 times the displacement. So you have whatever that numerical value that you have, and then divided by the time. So the time here would be like delta t and then delta t. So you have 2 times the delta t. So you have whatever numerical value that you have. So you can see that this basically illustrates that when velocity is a vector, and when vector comes with a magnitude and direction, when direction is considered, you might get a 0 value of the average velocity, while at the same time the average speed may not be 0. Actually, the average speed is non-zero because you always have a non-zero the total distance traveled by the object. Okay, so that's basically how you how the definition of average velocity and the definition of speed. So you can see that the speed, instantaneous speed, is basically delta x over delta t, the time derivative of the position. Okay, so we can interpret this as the velocity is the rate at which the particle's position is changing with time at a given instance, and it's also the derivative of x with respect to time, and also at any instance. Okay, let's say, take for example, at this point, the velocity is the slope of the particle at the point representing that instance. So that's if I want to find velocity at this point, then you draw, this is the point where you find the velocity. As opposed to when you find the average velocity, you're taking these 2 points to find the velocity. Okay, so you can see that this average velocity and instantaneous velocity, they are definitely not quite the same. Okay? All right, so what about speed? Speed itself, so this is definition of average speed. Okay? What about instantaneous speed? So instantaneous speed, we use s. So that's speed. We use s and just the magnitude of the velocity. Okay, so whatever that magnitude that you have, it's just the speed. Okay, so that covers the the definition of the the velocity, instantaneous velocity, the definition of this. What about acceleration? So when you have an object that's moving from this point to that, from x1 to x2, we know that it comes with a velocity because it's changing, it's moving, so it has a velocity. What about if it is moving not at a constant velocity? In other words, the velocity changes. When there's a velocity changes, it means that there is non-zero acceleration. So how do we define the definition? How do we define the acceleration? So again, just like velocity, we have the instantaneous acceleration. We also have the average acceleration. Okay, so how do we define that? So let me erase this. So the average acceleration is defined as this. So instead of taking the difference between the two position vectors, your average for acceleration is defined as this. And again, acceleration is also a vector, but because we're dealing with a one-dimensional case, so I'm not going to draw the vectors, the vector side. So you have the average acceleration, and that's equal to final velocity minus initial velocity over t2 minus t1. So you can see that in part it's very similar. The definition of average acceleration is very similar to the definition of average velocity. It's just that you replace the position with velocity. Okay? So in this case, this is just basically the change in velocity over the time interval that the change occur. So this is the definition of average acceleration. What about instantaneous acceleration? Again, sometimes we're not interested in the average value. We're more interested in knowing at this instant what is the acceleration, and then at the next instance what is the acceleration of the particle. So in that case, we're going to utilize the same procedures here. We're just going to assume take the interval, shrink the interval, time interval so small that the delta becomes differentiation value. Okay, so you have your A, dropping the AVG, then you have taking this, and then you have delta V over delta T. And so what you have here is that you can just, when delta becomes very small, it becomes dV over dt. So that's the definition of instantaneous acceleration, dV dt. Average acceleration, that's delta V over delta T. Okay? So what can we make out of this? Basically you can see that your acceleration is the time rate of change of velocity, and also it is a derivative of the velocity with respect to time. And if we actually plug in this, if we replace our V with this expression, what we have here is that you have d over dt, and your V here is dx over dt. And this basically is d squared x over dt squared. Okay? What does that mean? It means that acceleration is a second derivative of the position versus time. the first time derivative of velocity versus time, the second derivative of position versus time. That's the difference between acceleration. Now, if you're not familiar with the differentiation and also not familiar with the calculus, that is okay. This is just your, for your information. And also, our physics 311 is calculus based, so you should have some, understanding or have, or is taken or have taken math 140. So you should have some basic understanding of what's going on here. Okay. All right. So that's basically the definition of the acceleration and also the velocity, position, and displacement. So I'm going to stop here, and then we're going to go over the special case constant acceleration in the next recording.